Hello everyone, I'm Xinhan Cai from the MeDA lab at National Taiwan University. Okay. Today I'm delighted to be here and offer an introduction to the field of medical image registration. We will start by introducing the workflow of image registration. Following that, we will delve into each component within the workflow, covering the transformation, similarity, optimization, and finally, we will conclude with a tutorial. Okay, let's start by understanding what medical image registration is. Here we have two images. Okay, one is referred to as the fixed image, and the other one is moving image. The objective of registration is to transform the moving image and align it with the fixed image. For instance, in the figure here, the fixed image and the moving image are MR and CT image from the same patient, but they are oriented in a different direction. After the image registration, we refer to the resulting image as the warped image. The warped image is now aligned with the fixed image. Okay. Why is image registration is so important? We can identify the 5 potential use cases: making diagnosis, planning treatment, guiding treatment, monitoring disease progression, and comparing patient cohorts. To illustrate, consider the figure here. In the first column, we have T1 images captured from different views, showing the brain's structure. In the third column, the PET image reveals the lesion status. In the central column, we see the fusion of T1 and PET images, combining the advantages of both modalities. This image enhances the ability to make more informed decisions in various medical scenarios. Within medical imaging, we can categorize various registration types based on dimensionality, nature of the transformation, interaction, modalities, subject, and domain of transformation. As an example, consider monomodality, which involves the same modality. We can further distinguish between intra-subject and inter-subject scenarios. On the left-hand side, the two images are from the same patient and the same modality, MR. This situation might arise when the patient undergoes 2 MR scans within a year. After registration, doctors can efficiently compare the two images from comprehensive analysis. On the right-hand side, the 2 MR scans are from 2 different patients. This scenario may occur when we aim to align an individual's image with a standard brain or atlas for further research and analysis. Next, let's see multimodality. On the left-hand side, the MR and CT images are from the same patient. This situation may arise when a doctor requires additional information from different modalities to enhance diagnosis. And on the right-hand side, we see 2 images of different modalities. On the right-hand side, these 2 images are different modalities and from different patients. This application scenario is similar to the monomodality intersubject as shown in the previous page. In this context, we can align either an individual patient's image or multiple patients' images to a standard brand or atlas, facilitating the analysis of specific disease. Now let me introduce the workflow of image registration. To begin, we establish some notations. iMoving represents the moving image. iFix represents the fixed image. And iWarp is the transformed image. Commonly, we refer it as warp image. Additionally, T denotes the transformation, and S is the similarity function that quantifies the similarity between the two images. Suppose our goal is to align the moving image with the fixed image. In step 1, we apply the transformation T to the moving image, resulting in a warped image. Step 2, compute the loss, which is equivalent to the negative similarity. If the warped image and is close to the fixed image, then the similarity is large, leading to a small loss value. In step 3, if the process converges, the workflow outputs the optimized transformation and the warped image. If convergence is not achieved, the transformation is updated and the process returns to step 1. Essentially, it becomes an optimization problem. Understanding this process is very important in image registration. Okay, here is the simplified version, where we have highlighted the key components in the workflow: transformation, similarity, and optimization. In the following slides, we will explore each component in detail. Okay, transformation. Transformations can be categorized into linear and nonlinear transformations. In the context of linear transformation, we will explore rigid and affine transformations. The rigid transformations includes both rotations and translations. It preserves all distances, straightness of lines, and angles. For example, in a 2D rigid registration, we apply a rotation matrix to the coordinates vector and add a translation vector. This equation involves 3 parameters, including a rotation parameter theta and 2 translation parameters T1 and T2. For convenience, we often express the equation in homogeneous coordinates form, where the rigid registration can be represented as a matrix T multiplied by a vector x tilde. Moreover, in the 3D rigid registration, there are 6 parameters involved in the transformation. Okay. Now let's moving on to the affine transformation, an extension of the rigid transformation. It incorporates scaling and skews operations. We begin by introducing the scaling in combination with the rigid transformation. Scaling is represented as a diagonal matrix, which either enlarges or shrinks objects in each direction. Here, R is the rotation matrix and T is the translation vector. In a 3D case, it involves a total of 9 parameters, including 3 translation parameters, 3 rotations, and 3 scaling parameters. Now let's explore affine transformation, which preserves the straightness and the parallelism. But it does not preserve the distances and the angles. Okay. A finite transformation can be represented as x tilde equals ax plus t. There are 12 parameters involved in the 3D affine transformation. Moving on, let's see nonlinear transformation. Specifically, we will focus on the symmetric image normalization method, which is primary algorithm in the package we utilize for our tutorial. The algorithm is complicated, so I will provide an overview through this figure. Let's consider two images, I and J. First, the algorithm adopts a bidirectional approach, meaning image I is transformed to image J, and simultaneously, image J is also transformed to image I. Second, they conceptualize the transforming process as a timeline from time point 0 to time point 1, dividing it into multiple time points. Third, the transformed image at time point 0.5 should be consistent in both directions of transformation. In the transforming direction from I to J, the image at time point 0.5 is this one. And from training direction J to I, the time point 0.5 is this one. They should be identical. Finally, this algorithm ensures that the variations from time point 0 to time point 0.5 are consistent in both directions of transformation, which means these two variations should be identical. Now let's see the energy function, also known as the objective function. The function includes two terms. Let's see the second term first. When the transformed image I and J are identical at time point 0.5, the minimum is achieved. And moving on to the first term, it represents the variation in the direction from I to J from time point 0 to 0.5. And the other one represents the variation in direction from J to I during the same time period. The square symbol here indicates that the minimum occurs when both variations are identical. Okay, now we have discussed both linear and nonlinear transformations, but when should we apply linear transformation? And when is nonlinear transformation more appropriate? In brain images, for intra-subject registration, linear transformation is often suitable. This is because the shapes of brain tissues are relatively stable and don't deform significantly during breathing or changing in lying angles. On the other hand, in the inter-subject registration, where the shapes inside the brains of two patients differ, so nonlinear transformation becomes necessary to align them effectively. When applying nonlinear transformation, many algorithms are designed to initially apply linear transformation to roughly align the two images. Subsequently, nonlinear transformation is applied for finer alignment. This two-step approach helps achieve a more accurate and efficient registration. Now let's move on to the next component, similarity. We will discuss two types of similarity, feature-based and intensity-based. For this session, our focus will be on intensity-based similarity. In a feature-based similarity, annotated features such as points, lines, and contours are required. For instance, measuring the distance between corresponding points in the warp image and a fixed image serves as the similarity metric. Alternatively, the dice score of the segmentation in both warp image and fixed image can also measure the similarity. Features must meet specific assumptions. They should be landmarks visible in both images, and their locations are reliable, and they have ability of guiding the alignment. Intensity-based similarity involves optimizing some measures calculated directly from the voxels in images, eliminating the need for annotated landmarks, so making it an unsupervised method. We will focus on the four measurements, including sum of square intensity differences, sum of absolute intensity differences, correlation coefficient, and mutual information. Okay. For the sum of square intensity differences, we calculate the voxel-wise subtractions between image A and B plane, followed by the summation of the square values. This method tends to work well when only a small fraction of the voxels being aligned are likely to have changed between image acquisitions. However, it may fail if the data diverges too much from the ideal case. The effect of these outlier voxels can be reduced by using the sum of absolute differences. If the intensities in image A and B are linearly related, then correlation coefficient serves as the ideal similarity measure. This is particularly useful in intra-modality applications. However, the correlation coefficient may not be suitable for multimodality registration when intensities significantly differ, such as in MR to CT registration. In the figure here, it shows the correlation of intensities between different objects in CT and T2 images. Both CT and T2 images have low intensity values in air region, but CT has high intensity values in bones, while T2 still have low intensity in bones. This explains why the correlation coefficient fails for multimodality registration. Now, before introducing mutual information, it's important to understand the concept of self-information and entropy. Self-information is proportional to the uncertainty of an event. For instance, sunrise from the east indicates zero uncertainty, resulting in self-information equal to 0. On the other hand, the smart student failed the exam. This event has low probability because the smart student was expected to pass the exam. So the lower probability leads to higher self-information. The definition of the self-information is equal to negative log of the probability of the event X. In the graph here, we can observe that I of X, which is the self-information, is larger than 0 when the P of X is between 0 and 1. And when P of X equals to 1, then the I of X equals to 0, representing the lowest uncertainty. As P of X decrease, then the I of X increase. If P of X is a product of independent probabilities, P1 times P2, then I of X equals to I1 of X plus I2 of X. Next, let's discuss Shannon entropy, which developed as a part of communication theory in the 1940s. Entropy is a measure of the average uncertainty in a random variable, defined as the expected value of the self-information of a variable. For example, suppose there are 3 independent events A, B, and C. A occurs when probability 1/2, B occurs when probability 1/4, and C occurs when probability 1/4. Then the entropy will be equal to 1.5. Next, let's discuss how to calculate the entropy of an image. Consider an image with pixel values shown in this figure. First, we create a histogram for each pixel value. For example, there are 2 pixels larger or equal to 0. These 2. So this space has 2 components. Second, divide the counts by the total number of pixels. This gives us the relative frequency, which represents the probability density function. And finally, we apply the definition of entropy to calculate the entropy of the image. Next, let's discuss how to calculate the joint entropy of 2 images. For example, suppose U and V are 2 images. Begin by identifying the joint intensities of 2 images. 1, 1 here, and 3, 1 here, and 0, 3 here, and so on. Then compute the histogram for these joint intensities. For example, there are 2, 1, 1 in the joint intensities. So there are 2 points in the coordinates 1, 1 in the histogram. Utilizing this histogram, we can derive the relative frequencies and finally apply the definition of entropy to compute the joint entropy of the 2 images. Here is the visualization of a joint histogram. On the left-hand side, image X and Y are identical, resulting in a joint histogram that forms a diagonal matrix. On the other side, when image Y is rotated, then the joint histogram becomes more complicated. Now, based on entropy and joint entropy, we can compute mutual information. Please refer to the figure here. H of A represents the entropy of image A. H of B prime represents the entropy of image B prime, and H of A B prime represents the joint entropy of image A and B prime. The mutual information I of A B prime is represented by the overlapping region. From the information aspect, the larger mutual information value indicates a greater amount of shared information between the two images. Finally, the optimization approach. The optimization process can be addressed using gradient-based algorithms. To prevent local minimum, a multi-resolution approach is implemented. Initially, the optimization of the transformation is iterated on a low-resolution image. After a certain number of iterations, the optimization is then applied to a higher resolution image, and so on. Combining the strategy we have mentioned before, the complete registration process involves optimizing linear registration with a multi-resolution strategy first, then followed by optimizing nonlinear registration using the same multi-resolution approach. Now let's have a tutorial. Okay. There are several open source registration packages available, such as ITK, Simple ITK, ANTS, 3D Slicer, FSL, and SPM. We have two multimodality tutorials today, one for intra-subject, involving images from the same patient, and the other one for inter-subject, dealing with images from two different patients. Now please add the data shortcut to your drive, clicking the link provided here. So you can do it now. After you click the shortcut here, you should see the web page like this. And please click the link again. And then click Rich Data, Organize, Add Shortcut. And please select all locations, My Drive, and click Add. Okay. When you have done this process, you can click the link below the collab here and click Copy to Drive in the web page here. So I will give you 3 minutes to do these.为什么可以延伸荧幕？
没有变延伸荧幕？
你有换？
有啊，我刚刚就是，不然我得调一下，是哪一个？
显示。
显示这样。
显示提供。
啊，对对对。镜像输出。样子 OK， 好，感谢感谢。Okay, now let's start the tutorial. You can click the button here to extend the table of contents. Now you can see we have two examples here. One is intra-subject, and the other one is inter-subject tutorial. Okay. 放大一点哈。Oh, okay. First one, install, and you can, to execute the cell, you can press Shift and the Enter button, or you can just click the Run All button here to run all the cells. Okay, in the first cell, it needs you permit the notebook to access your Google Drive files. So click the connect to Google Drive and accept it. Okay. Next cell, install the AMPSS package. Okay, you will download in the package and install it. Okay, and next cell, we import these 4 packages. And before the registration, please make sure you have added a shortcut to your drive, the data shortcut. Okay, we have two functions. We have defined 2 functions here. This one, clip intensity function. It clips the image based on the window level and window width. And the function visualization can show some slices of the scan. And let's define the path of the images. Please note that we assume you have created a shortcut in your drive. Okay. And read the images by AMPSS.ImageRead. CT007, CT007 move, and MR007 are from the same patient. Okay. MNI 152 is the standard brain image, and the MNI 152 seg is the segmentation mask of the standard brain. Before registration, we resample all images. Let's see the printout result. We can see the dimensions of the CT image is 164, 194, and 142. The dimensions of the standard brain are 193, 229, and 193. And they all have the spacing 111. Okay, in example 1, we perform intra-subject multi-modality registration. In step 1, we set the fixed image and the moving image. And in step 2, we visualize the images before registration. In step 3, we apply rigid registration. And in step 4, we visualize the images after registration. Oh, okay. We set the MR image as a fixed image and CT moving image as a moving image. And we also clip the moving image, which is a CT image. We keep its intensity and save it as a clipped moving image. Before registration, let's visualize the fixed image, moving image, and clip moving images. It's apparent that the fixed image and the moving image have different orientations. The clip moving image the clip moving image allows us to observe details inside the skull. And in step 3, we apply rigid registration. And we apply the rigid registration by nth-start registration and set the type of transform as rigid. Okay. The result is a dictionary. Including warp move out, warp fix out, forward transforms, and inverse transforms. Warp move out is the warp image computed by T of I moving. Okay, and warp fix out is the image computed by T inverse of I fixed. Okay, and forward transforms here is the list of the paths. It's a list of temporarily saved paths of the forward transformation T. And the inverse transformations is the list of temporarily saved paths of the inverse transformation T inverse. Okay, in step 4, let's visualize the registration results. As you can see, the warped image is now aligned with the fixed image. Next, in example 2, we have a tutorial for inter-subject multimodality registration. The steps are similar to example 1, with the key difference being the utilization of the nonlinear transformation. First, we set the fixed image and the moving image. We set the standard brand MNI 152 as the fixed image and the CT image as a moving image. And we also have a clipped moving image. Now, as you can see from the visualization of the fixed image and the clipped moving image, they are different in size and shape because there are two different patients. The first row is the standard brand or atlas, and the second row is the patient. So they are very different. Oh. Sorry, because the internet is broken, so we have to rerun all the cells again. The nonlinear registration may take 1 minute or 2 minutes. Okay, let's continue. We set a type of transform as SYN, which is nonlinear. Please note that the process includes both linear transformation and nonlinear transformation, optimized through a multi-resolution approach, as we mentioned before in the slide. As you can see, okay, it finished. As you can see, the forward transforms here. It is a list type, and it contains 2 paths. This one is the affine transformation, and this one is the nonlinear transformation. Okay, except the 2 transformations in these 2 temporary paths, and the inverse transformation we also have 2 paths here. And finally, in step 4, we can see the warp image is aligned to the fixed image now. The fixed image, the first row is the standard brand fixed image, and the second row is the warp image. So this is the visualization after registration. And before the registration, they are very different. And after the registration, they are very similar. Okay. And finally, we have a segmentation. So far, we observed that the registration approach we used is unsupervised. Next, we show the unsupervised segmentation by image registration. Okay, suppose we have the atlas or standard brand and its segmentation mask. Then we can derive segmentation masks for any patient. Note that this method is applicable when precise segmentation is not required. Okay. iFix is an image of the atlas, and MFix is a segmentation mask of the atlas. These 2 are already known. Okay, and moving is the desired segmentation mask of the moving image, which is the objective mask we want to derive. Okay. Now, in the previous steps, in the previous registration steps, we already have this one. T of I moving, I warped equals to T of I moving. And we just need to use the inverse transformation to transform the M fixed to the M moving. So let's see the visualization result. Okay. The atlas image and its segmentation masks are shown in the first row. Because we have aligned the moving image to the atlas, so we derive the warp image and its segmentation mask which is actually is N fixed. And finally, we apply T inverse to the transformation, to the transform N fixed to N moving, so that we derive the segmentation of the moving image. Note that the registration might not be accurate. If you have annotated data, training a deep learning model in a supervised manner is a better approach. And thank you for your listening.